Okay, everybody. Well, we're about ready to get started. Only got a couple of people watching so far. So the people that are here, can you hear me? So again, can you hear me if you're out there? All right. All right, so let's go ahead and get started, guys. So we got an action-packed hour here that we're going to be doing. I will try to go at the best speed that I can go. There's a lot of stuff that I really want to get to. I printed off 16 questions, I think, so hopefully you got all those from the Google Classroom. You can find all those. And again, the point of this is try to cover as much as we can in this hour. And if you want to go back and watch anything, feel free to do that. The video will be posted, right after. So let's dive right into this. A lot of people asked me to go over some of the earlier topics, so that's what I've decided to do for the most part, and then try to transition into the newer ones. So here we go. So the first one that we have, and a lot of these questions I'll probably just try to read through them pretty quickly, and then I'm just going to go on. So if you're trying to take notes, that's totally fine, but again, you might find it's better to just go get those later. And if I heard I was someone's dinner guest last time, so if, again, I'm anybody's dinner guest tonight, that's awesome. Um, let's do it. So Alzheimer's disease results in a loss of cognitive ability beyond what is expected with typical aging. A local newspaper published an article with the following headline: Study finds strong association between smoking and Alzheimer's. The article tracked 2,100 people for 23 years, and the article stated for those who smoke at least 2 packs a day, the risk of developing Alzheimer's was 2.57 um, times the risk for those who do not smoke. So identify the explanatory variable and the response variables. So I just have a couple of things that I want to go over here in this problem. So the first thing that we have is what is our explanatory variable? And again, I'm just going to kind of read through these. So an explanatory variable is the variable that explains changes in some other variable, which is known as our response. And that is usually our outcome of the study, what we're interested in seeing happen. Okay? So the explanatory variable also goes by a couple of other names, and this is very important. Sometimes it's called a factor. Sometimes we call it an explanatory variable. Sometimes it's a treatment, but other times it's not necessarily just a treatment, and I'll explain what that means. Factors sometimes have different levels, which are different strengths of the factor. So for instance, I drew one here. We have aspirin, that would be a factor. This is a different study, totally, by the way. It could be administered at 30 milligrams or 100 milligrams. So we have 2 levels inside of this factor. Vitamin C is another factor. It could be administered at 0, 50, or 500 milligrams. So vitamin C would have 3 levels then. Now, how does this work to combine to give the treatments? Well, then that would make us, we would multiply the levels. So 2 times 3 leaves us with 6. So 1, 2, 3, 4, 5, 6. So treatment 5, for instance, says that that person received 50 milligrams of vitamin C and 100 milligrams of aspirin. So I said up here, sometimes we call factors, explanatory variables, treatments. If there's only one factor, then that's also going to be the same as the treatment. But if there's multiple factors, they will multiply to give you the treatments. Okay, so let's go take a look at our problem now and see. The explanatory variable in this case was what were we hoping, well, sometimes it's easy to start with the response. What was going to be the outcome of the study? And we were trying to see what's the probability or the likelihood that they would develop Alzheimer's. And I hope you guys are just thinking, developing Alzheimer's, would that be categorical or quantitative? Well, how would someone answer that? They would say yes or no. So that would be a categorical variable. Okay? The explanatory variable in this case would be how many cigarettes do you smoke? So actually, the article states for those who smoke 2 packs of cigarettes. So it would be do you smoke or not, or smoking. more than 2 packs of cigarettes. Okay, so we can see there's our explanatory, and our response is the outcome. Okay, is this study described an observational study or an experiment? Real basic. Remember, an experiment is one in which we impose a treatment on a group of subjects or experimental units. Experimental units are the smallest unit receiving treatment. Okay. Now, in this case, I don't have experience. Okay, so actually, let me answer this question first. So, do we have an experiment or observational study? Did I make anybody smoke cigarettes? No. So, therefore, it is an observational study. We merely observed who smoked and who didn't. This is not an experiment. An experiment would impose that treatment, would make people smoke, which obviously is unethical. Okay? So this case, because it's observational studies, then each of my 21,000 patients were observational units. If this was an experiment, those would be my experimental units. Okay? All right, and the last question. Exercise status, regular weekly exercise versus no exercise, was mentioned in the article as a possible confounding variable. So how can it be confounding? Now remember, a confounding variable is a variable that attaches to one treatment group. This is so important and causes changes in the response. But we're unable to tell if the change in the response is due to the confounding variable or the explanatory variable. So that is the question. It must attach itself to the group. So you must take a look at this and figure out, how could exercise tie to a group? Well, who's going to be more likely to exercise? People who don't smoke. Okay, does that make sense? So here's what we need to say. We now need to say how it's confounding. People who don't smoke would be more likely to exercise. Do you see how I've attached exercise to this group? Okay, and again, you don't have to know this, just have to tie it in. You don't have to know anything about smoking and exercise. Therefore, we'd be unable to tell if changes in Alzheimer's were due to smoking, to not smoking or exercise. So what I've done is I've attached that to the group, and that's the part that's really important here. Okay? To be confounding, it must attach. If it doesn't attach to one specific group, that's another variable. We don't talk about that one because that's one that's really hard to get right on the AP test. But you just say potential confounding variables is the way that you want to word that. Okay. Okay, that's our first one. Let's move on to our next one. Okay, number 2. So, and I'll just wait for a question here, see if anybody has a question. All right, so number 2, in search of mosquito repellent that is safer than ones currently on the market, scientists have developed a new compound that is rated as less toxic than the current, thus making a repellent that contains new compounds safer for humans. Scientists also believe the repellent containing the new compound will be more effective than the ones in the current. To test effectiveness, they take 100 people and they have 100 bins filled with mosquitoes. Okay, so we've looked at this one before in class, but it's a good one to talk about. So A, suppose the study is conducted using a completely randomized design. So a completely randomized design brings nothing else into account except for randomization. We take every person that we have, we put them, all their names into a hat. So in this scenario, put 100 names in the hat and mix well. pull out the first 50 names to receive the new compound. The remaining 50 get the old compound. Each person, and that's my experimental unit, just from before, just to review, put their arm into a bin, and then we will compare the average number of bites with the new versus the old. Okay? And I just put in here what type of test this would be. I have 2 random samples, so I randomly assigned to 2 different groups, so it would be a 2-sample t-test. In picture form, we take the 100 people, randomly assigned to the 2 groups, and then we just compare. Now you got to remember, the 3 parts of an experiment are randomization, replication, and control. Randomization is going to balance out all uncontrolled factors in the study. Maybe some people have sweet skin. Randomization should balance it out. Maybe someone ate garlic that day. Randomization should balance that out. Okay. Replication says do it to a lot of people. 100 is a lot. And control says control for everything else, like how much they put on, etc., etc., etc. Okay. All right. Then in the next one, I made this one up, but I just said A2. Imagine that they said females were more likely to get bit than males. Okay, so imagine that they said this. Obviously, this probably isn't true, but who knows? You never know. So now we want to create a randomized block design. Again, I added this question in. So what would a randomized block design look like? So I just tried to draw this out for a picture. We take our 100 experimental units. We then break them into males and females. Then we put all the males' names in a hat and mix it well. Pull out the first 25 to get new, 25 to get old. Do the same with females. 25 new, 25 old. Now look, each group has the same number of males and females. Now randomization should balance it out up here, but maybe it won't. So this guarantees to be balanced out, and this guarantees that if that is a value that affects the response, then that will reduce variability there. Okay? Alright, going back to the question, the original question. Part B said, suppose that the study is to be conducted using a matched pairs design. Describe a randomization process and identify an inference procedure for the study. So remember, in a matched pairs design, each person will receive both treatment, or you can match someone up as closely as possible. But in this scenario, we're going to use each person. Everybody's got 2 arms. So each person will receive both the new and the old. So for each person, we'll flip a coin. If it's heads, they'll get the new on their right arm. Tails, they'll get new on their left arm. So I've now said what the coin will do. I have to make sure that I assign both treatments, so the other arm will receive the other treatment. There we go. Each person will then put their right arm in first, take it out, then put their left arm in, and we'll compare the difference in the number of bites. This would be a matched pairs t-test, because now I would be interested in finding mu d, the true mean of the differences. Okay? So that would be the inference procedure there, matched pairs t-test. And we're going to talk about that a little bit more. And then question C says, which one is better? Obviously B is going to be better. Matched pairs is going to reduce variability. Everybody's the exact same as themselves, so we don't need to leave it up to randomization to try to balance it out. We can make sure that everyone is the same as closely as possible. Alright, questions on this one? I'll pause for a second. Okay, nothing coming through, so we'll keep moving on then. Alright, number 3 in my packet. So here's what we got for this one. Again, you've seen this one too, but it's okay. At the end of the day, an apartment building has 9 floors, and each floor has 4 apartments. The building owner wants to install new carpeting in 8 apartments to see how well it wears before she decides to replace it. The figure below shows the apartment numbers. The 9 with asterisks indicate children. So why did they tell you that? Obviously, that's going to play a part into the problem. Otherwise, they wouldn't have said anything. So here's the first floor, second floor, third floor, fourth floor. So for convenience, the apartment building wants to use a cluster. All right. So this is telling us this is an observational study. Okay. So let's talk about our observational studies real quick because we just went over our experiments. Okay, the first one that we have, simple random sample. The definition is every group of n items has an equally likely chance of being selected. Easiest idea, put it into hat. It doesn't matter anything else. Okay. Stratified. We divide the population into homogeneous groups, then take a random sample from each strata, and then combine. This can reduce variability because you're going to have similarities from sample to sample. Cluster. The population is divided into heterogeneous groups, which means they're well mixed. Everyone's in each cluster. These are natural, never make them. And then you randomly select a cluster and survey everyone in the cluster. That's our big thing. So anytime you see, a good method where they're randomly selected and you survey everyone, that's screaming to you that it's a cluster. And systematic is where we randomly select every nth person. Okay? So again, I know I'm going fast. You can go back after and pause this and feel free to write any of these things down. So they wanted a cluster sample, and they want each floor to represent a cluster. So if there's 4 apartments on each floor, and we want 8 apartments, guess how many floors we want to pick? 2. And when I pick 2 floors, guess what? I'm going to survey every apartment on the floor. So here's what I'm going to do. Put the numbers 1 through 9 in a hat. Mix well. That's a mix well. Pull out the first 2 without repeats, and we will install the new carpet on every apartment on those 2 floors. Okay, so we can see how that's going to work out. Okay, next one, B. An alternative sampling would be stratified, where the strata are the apartments with kids and without kids. So how would I do a stratified? That's not what this is asking, but I would take all the apartments with kids. So for instance, all the kids ones would be 11, 22, 23, 51, 74, 73, 84, 92, 93. Put them in a hat. Mix well. And we're going to pick 2. That's what they told us. Okay? Then we'll take all the non-kids, and again, put those in a hat. So that'd be like 12, 13, 14, blah, 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 blah. And then we'll pick 6. Okay? So what is the benefit of that? Why would that actually be better than the previous one? And you have to think about why it would be an advantage. You have to be so clear on the AP test. What do you know about kids? Kids will wear the carpet down. Okay, so that's going to be the factor. So what's the benefit of this method? Stratified guarantees that we will have apartments with kids and without kids. With and without kids, right? It guarantees I'm going to have 6 without and 2 with. Why wasn't that guaranteed in a cluster? In a cluster sample, we could have gotten picked floors 3, 4, or 6 with no kids. Okay, so you said the benefit, right? You said why it's different, but why does that matter? Remember, you got to bring this thing full circle. Apartments with and without kids, apartments with kids will wear the carpet differently. Do you see how now I brought this around to the response? I said, what about that is going to affect the response? Kids will wear the carpet differently. And there we go. Okay? So there's all of our review for this is basically the first unit that we did in class with our experimental design. Okay, so hopefully you got a good run through with all of those. Okay, moving on to the next one. Okay, so next one I've got is graph, and I'm not going to spend, again, a ton of time on the graphs. I'm really just going to kind of talk more or less about the main ideas here. Okay, so what do we have? Again, we have a histogram. Histograms are good for quantitative data. And remember, it created bins. So again, this is probably 0 to 2.5. This is tip amounts. So Rob works as a server where she can earn tip. If each customer she serves, the histogram shows the distribution over 60 tip amounts. So we know n is 60. And not that it necessarily matters, but maybe it does. So that means there's 25 different tables, I guess, in which she earned a tip between $0 and $2.50. That's not very good. 22 times she earned between $2.50 and $5. Now this would probably be inclusive on 0, not inclusive on 2.5. So just so you're aware, you have to have the same width on each. So write a few sentences to describe the distribution of tip amounts for the day shown. So what we need to do now is we need to, anytime we're asked to describe a distribution, we need to talk about the shape, the center, and the spread. So, and there needs to be in context, and don't sound like a robot, okay? So the distribution of Robin's tips in this scenario would be skewed to the right. She has an outlier at over $20. That's a good one. It probably made her day. And maybe I'll put that in there. Okay, we need to talk about the center of the distribution. In this scenario, I would probably find the median. To find the median, the location, you do 60 plus 1, n plus 1 divided by 2, which is 31, which would be 30.5. So that tells me that the median is between $2.50 and $5. So her median tip is between 2.5 and $5, which again, not the greatest. Hopefully she has lots of tables. And last thing we need to mention is the spread. We could say that I would go with range. The data has a lot of variability. With a large range of, I mean, we have to approximate it of, about 20. Hopefully there's no $0 tips. Okay, so shape, center, spread, outliers. Got it. Easy peasy. Just talk about it in context, which is what I did. Okay, part B says one of the tip amounts was 8. If the $8 had been 18, what effect would the increase have had on the following statistics? So we take 8, which, if we notice, 8 is in here, which is above the median. And I'm going to move it further to the right. Well, what kind of an effect would that have? Well, that would make the mean larger. Because the mean is not resistant. And I could actually tell you, it increased by $10. So divide by, there was 60, so it increased technically by 60 cents. Actually, let's see, $10 divided by 60. Actually, I don't know how much that would be. Can't do that in my head. Okay, the median would stay the same. $8 is above the median, and so is 18. It is a resistant measure. So remember, anytime you have skewed data, you want to report the mean. Just kidding, you want to report the median as center, and the IQR is the spread. If you have a symmetric distribution, mean for center, and standard deviation for spread. Okay? Alright, moving on. Hopefully you guys are finding this useful again. I know we're trucking right along here. 4 questions in, about 6 minutes each, so not too bad. Remember, for the AP test, you got about 10 minutes for each of these questions. So what I did in this one, and I don't think we're going to really write this, maybe we'll write it out real fast just because people have a hard time. So we've got Corporation A, Corporation B. Don't even worry about reading it. It's how much the starting salaries are. So write a few sentences comparing the distributions of yearly salaries for the two corporations. So we need to compare these box plots. Okay, when I compare box plots, guess what I need to talk about? Shape, outliers, center, and spread. And I just need to use comparative language. So if I look at both of these, starting off, the shape, so corporation A would be skewed to the right, starting salaries. Well, B is skewed left, slightly skewed left. And if you understand what skewedness means, that means that you have, remember, there's the same number of values in each box. In each of the quartiles from here to here, and here to here, and here to here, and here to here has the same number of values. I'm not saying that these two have the same. Let's see, at each, actually there was 30, so they would each have the same. Okay? So, what do we notice about these values? They're closer together, and that's what creates this skewed to the right. The right side gets pulled out. This one has the values close together. That one's skewed to the left. Okay, so corporation A, for outliers, has two outliers at 70 and 80,000. It's a nice starting salary. That's about, I don't even think that's my 30th year of salary. Center, now we want to compare the centers. Both groups have the same median. At 50K. And the spread, let's see, corporation A would have more variability because they have a larger IQR and a larger range. So corporation A has larger range and IQR, meaning more variability. Okay, and so that's basically what we need to ask there. Okay, shape, center, spread, outliers, context, comparative language, more, less than, all that good stuff. So now B says, suppose they each offered you a job for $36,000. Based on the box plots, give one reason why you might choose to accept the job at corporation A. Well, if you're starting at $36,000, you can only go up with your salary, right? You can see everybody else is making a lot more, so you might have more of a chance to make more later on. Why might you choose the corporation at B? Well, if we look at B, we might choose B because everyone is more consistent. So in A, you've got some people that are making way more than others. B, everybody's consistent with less variability, so you might choose to go there. All right? Again, you would want to come up with something that fits in with the context. Okay, moving on. Okay, number 6. Okay, so here's what we got. This is whether you reside on or off campus and whether you participate in any activities. Okay, so when you go to college, you can either live on campus or live off. So calculate the proportion of on-campus students in the sample who are in at least one extracurricular activity and the proportion of off-campus who are in at least one. So that means I want to find the probability, given that you're on campus, that you're in at least one. Okay, so I want at least one. So you could be in 1 or 2. I want to look at this column versus this column. Would you guys agree with that? So at least 1 would be 24 out of, how many people live on campus? 33, not on campus, but from our sample. What about the off-campus group? Well, that would be 37 out of 67. So we can clearly see that these two values are very different. I'm not going to calculate them out. It doesn't really matter. So then in letter B, they now give us 100 students are summarized in the segmented bar graph. Now remember, segmented bar graphs are for categorical data. Okay, so they're for categorical data. And whenever you compare categorical data, bar graphs, You simply want to talk about a similarity and a difference between the two groups. So, in this scenario, what would be the similarity between the two? Let's see. So if we take a look at these, we could see in both of them that two or more students doing two or more activities was least likely. Okay, so there you go. So we could do something like that. And what would a similarity be? Well, again, actually that's our similarity. Our big difference would be students that are in off-campus are less likely to participate. Are less likely to participate than on campus. All right, something along those lines. But again, we're looking for a similarity and a difference is the main thing that we're going to be focused on in that one. Okay? All right. So let's go, and then I'll take a break after the next one to see if you guys have any questions. I am checking the questions. Nothing's coming in yet. All right. I love this one. Political party. Thankfully, they use W, X, and Y, right? And gender, male and female. So we can see how this was taken. This was a registration by all 500 registered voters. So this is the population. So these would be parameters. It's always important to understand, right? Statistics versus parameters. Statistics are samples, parameters, populations. So part A, given that a randomly selected registered voter is a male. Oh yes, is a male. What's the probability that he's registered for party Y? So probability, given that it's a male, remember that always comes second, that he's registered for Y. If you look at your formula sheet, you'll see this right on there. That's the probability that it's a Y and a male divided by a male. So Y and a male, there's 48 of them. Divided by all the males, there was 200 of them. I believe that's 0.24. There you go, easy. Among registered voters, are the events male and Y independent? Justify your answers. All right. Well, if you remember what it means to be independent, that means knowing one event doesn't affect the other event. So A given B is equal to A, or you could do A and B is A times B. Either way, both will give you the same solution. Now, this is population data, so it has to be the same. If you think about a chi-square of independence, that's a sample data, and you're trying to assess the population based off the sample. So I'm going to do this. The value that I just calculated is going to help us out. Y given male. If it was independent, then being a male shouldn't affect whether you're in Y. And remember, these first values have to be the same. This is the event. This is the given. I want the events to be the same. So I just found this. This was 0.24. The probability that you're in political party Y is 168 out of 500, which is 0.336, I think. Does that equal the same thing? Pretty sure that's right. Are those the same values? No, they're not the same values. So guess what that tells us? That they can't be independent, right? If you are a male, you are much more likely to be, actually, sorry, if you are a male, knowing you're a male, you're less likely to be in political party Y. So knowing you're a male makes it less likely to be in. Why did I say that? Because 33% of people were in Y. But all of the males, only 24%. So that value changed. Okay? All right. C, I love this one. What if they were independent? So here's what their bar graph looked like. Remember, categorical data. If I had to compare it, right, segmented bar graph, you divide by 100, right? This is good for comparing, and it's proportions for comparing different sample sizes. So we see that they're different, right? That tells us that they're not independent. So what would it look like if they were independent? And this is where people get this a little confused. Is anyone saying that the rates of being in W, X, and Y have to be the same? No. Independence across gender means that all the people in W, the proportion of people in W, should be the same for males and females. And the proportion of people in party X should be the same for males and females. And the proportion in Y should be the same for males and females. That's what independence is really talking about. That this proportion and this proportion are the same. This one and this one, this one and this one. Not X, Y, and Z. Nobody said that had to be true. W, X, Y. I'll get the variables right. Okay, I'll pause for a question. Elizabeth, I see you posted nope. Any chance you could elaborate on that? Maybe it's in response to the thank you for being here. All right, there's a little delay, so I'm going to keep moving on, otherwise it's going to take forever. All right, so I want to do another probability one here with everybody. So let's go ahead and take a look at this one. Again, moving on to the next one. I've added in a question at the bottom of this one. So the variable is the number of ATMs working when the mall opens. Oh, all right. Oh, I got you. Thanks for answering the question. Okay, so so what's the probability that and so remember 0, 1, 2, 3, okay? And the probability 0.15, 0.21, 0.4, 0.24. Okay, so remember how that works out. Remember, for a correct probability distribution, all the probabilities have to add to give 1. So letter A, what's the probability at least one ATM is working? Okay, so all we have to do is look at it. At least one. So that means I could have 1, 2, or 3. So guess what I have to do? Add this plus that plus that. It's just that simple. So it'd be 0.21 plus 0.40 plus 0.24, and that's 0.85. Okay, so there we go. So the probability at least one is 0.85. That's an easy question. Okay, B, what's the expected value? We spent time on expected value. We reviewed that in the last video. We've reviewed that in class. That formula is on your formula sheet, so we know that that's there. Remember, the expected value, or the mean, is each value multiplied by the probability. So what we need to do here then is simply do 0 times 0.15 plus 2 times, 1 times 0.21 plus 2 times 0.4 plus 3 times 0.24. I have no idea what that is, but that's it. Okay. Don't forget how to run your 1-var stats as well. You could plug it into lists and do your 1-var stats. You just have to make sure that you put the frequency list. Okay, let me just run through that real fast just to make sure that everybody is okay with how to do that. So we would add a page here, and we do a name, and then probability. And I'm just going to do this real fast. I'm just going to do 1 and 2. So it's not this problem, so understand. And I'm just going to say 0.25 and 0.75. So to get the mean or expected value out of one of these, you just go menu, stat calculations. This is where you always get the mean, right? Or linear regression, 1-var stats, and we have one list. The trick here is that we have X list is our variable, and then you change the frequency list to their probability. And then that will give you your correct mean, and your standard deviation is sigma. Okay, so just so you guys are all good with that. All right, letter C. What's the probability that all 3 ATMs are working when the mall opens, given that at least one ATM is working? Okay, so this always sounds hard, but it's not bad. Just try to write it. You see given. You know that that comes second, so at least one. Hey, well, I just found the probability at least one is working right there, so I'm probably going to use that. And 3 are working, all 3. And I know this is the probability that 3 are working and at least one. That's talking about the same thing. If at least one's working, if 3 are working, at least one's working. So I don't even need to worry about this in any special scenario. And at least one is the denominator. I'm just going to put one, yeah, at 1. So all I care about, 3 and at least 1, look, that's just 0.24. That doesn't change. If at least 3 are working, that also is at least 1. So that's why that and is good. And at least 1 you just told me was 0.85. So then I do that math, and I come up with 0.282. So then this problem gets a little tricky for D. And it says, hey, given that at least one ATM is working, what would the expected value of the number of ATMs that are working be? Less than, equal to, or greater than the expected value from part B? Well, I actually didn't do that because I didn't read that question the right way, but I created the whole new probability distribution. So look, 1 given at least 1 is 0.21 out of 0.85, 0.247. And 2 given at least 1 is 0.4 out of 0.85, 0.4076. And 3 given at least 1, 0.24 out of 0.85. We just found that one. Now, do these all add up to give 1? If they do, then that's how we know we have the right probability distribution. And they do, I checked it. And so now I could find the expected value. But guess what? This expected value would be larger. Why? There's no 0 to pull down the mean. So that's all you had to do. You didn't really have to create that distribution, but I always think that that's a good little review just to go back, because that one might throw some people off. Okay, there's a good probability one. All right, about 19 minutes left. We're doing good on time here. Oh, letter E. I almost skipped this one. And I just wrote this in because this is one that people always have a tough time with, and people ask for this question. So if we take a random sample of 10 days, what's the probability that 0 ATMs are working? So now, 0 ATMs are working exactly 1 of the 10 days. I know it's worded weird, I just made it up really fast. Okay, what's the probability that 0 ATMs are working? 0.15. I just look at my table and find 0.15. What did they tell us here? They gave us an n. They said n was 10. Probability of success is 0.15. Guys, what is this setting me up for? And this is setting me up for a binomial problem. So remember, for binomial, we have our bins. Bi means 2 outcomes. I independent. N number of trials is fixed. S same probability of success. Okay? So if I want to find the probability that exactly 1 day it's not working, then I would do 10 choose 1 times 0.15 to the first, because I'd have 1 not working, and 0.85 would be the other 9 days to the 9th power. And that would be a binomial PDF in the calculator. If you go back and then look at the question, again, I was just doing it quick, but it says, what's probably that at least 1 day 0 are not working? So greater than or equal to 1. That's where binom CDF is going to come in. N is 10, P is 0.15. In this scenario, you put the lowest 10, as the lowest 1 is the highest 10. So it'd be a binom CDF. That would add up y equals 1 plus y equals 2 plus y equals 3, blah, 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 all the way up to 10. And then I just tried to be tricky here, and I said more than 1, so then my low would switch to what? 2. So more than 1, the low would switch to 2. So this would be y is greater than 1. Okay, so there's a good little binomial review. All right. Moving on to the next one. All right, so we're getting into some tests now. So really, if you think what we covered so far, we've done graphs, we've done experimental design, we've done probability. I did not do anything with normal distribution or sampling distribution today. So that was kind of hit in some of the other videos. And again, I think that's an easy enough one to search. And I kind of wanted to talk about after class, I wanted to talk about a couple of things that I've just been seeing going on in class. So I want to really focus on this one, on the difference between a 2-sample test and a matched pairs. So at any rate, there's a whole lot of wording going on up here. But we see we have Group A received a placebo. Group B received a cholesterol drug. And what we were interested in is how much was there a reduction in cholesterol. Okay? So do the data provide convincing evidence at an alpha of 0.01 that the cholesterol drug is effective in producing a reduction? Okay, so here we go. So we need to look at this, everyone, and we need to decide, In my data, this is clearly quantitative. I can find the average mean reduction. Look, they did it. So you know it has to be quantitative. So when I have this, I now need to determine, do I have a two-sample t-test or a matched pairs t-test? So what we need to ask ourselves is this person independent of this person? Is this person independent of this person? Did they give us any link to say that those two people were similar? Well, no. In the problem, 10 of the 20 males were randomly assigned to the group. So I know that this person is not connected, and this person is not connected. So therefore, these two groups would be independent from one another, and that's what the random assignment did. So this tells me that this is a two-sample t-test. And I'm just going to quickly go through some parts of this just so you can see just a couple of things. So remember, we use phantoms, and I'm not going to go through, but we've got to do our parameters. So mu A would be the true mean reduction of all patients receiving the placebo. True mean reduction of, I should put really what it was, of cholesterol. And mu B is blah, 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 right? But this is no longer placebo, now it's the drug. Okay, so I'm just going to grab a couple of things here. So my H would be my hypothesis, so our HO would be mu A equals mu B. My HA would be mu A is greater than mu B because we want B to be reduced. Okay, so you could do that the other way if you wanted to. Okay, assess the conditions. So we were told they randomly assigned the treatments. Okay, the second one that I need is normality. So I now need to go through and check normality. So how do I check normality? They didn't give me the graphs. My sample size isn't big, right? It's 10. If it was bigger than 25, we could have approximate normal with central limit theorem, but it's not. So we need to go and do the graphs. So I just wanted to review this because it's been a little while. I put my data in two lists. So my data is right in there. And I can get my, I'm going to do two graphs. So I'm going to do, there's my AAA. And remember what kind of graph I want to assess normality. A normal probability plot. So menu, plot type, normal probability plot. Remember, we're looking, does it follow the linear pattern? And you'd have to show that on your paper. Bing, 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 bing. I'm making it up. And I've got to do the other one too. So I'm going to do both at the same time. So I change that to BBB. Ah, there we go. Okay. Also follows the linear pattern. Now remember, this isn't linear data. This is normal probability plot. So we'd say both NPPs show linear patterns, and I'd write it out on the AP test, normal probability plot. Show linear patterns. So we can assume both populations are approximately normal. Look at what I said there. Populations are approximately normal. That's what we need, right? We need the populations to be approximately normal. If the sample is approximately normal, then it seems like the population could be. Okay, name the test. Two-sample t-test. Okay, and again, why do we use t, not z? Do we know sigmas? No, we have s's, the sample standard deviations. So from this point, I'm just going to go, I'm going to show the test statistic, but if I were you guys, unless you really know it, I would just put, I'll show you what I put. If I were just you and you weren't that comfortable, I'd ignore all that, and I would just go straight to running your test. And I'm just going to do that just again for a quick little review in case anybody out there is not sure how to do that tonight. So remember, we just go, okay, first blank column, first blank row, menu, stat tests, and we're going to go two-sample t-test. And we've got the data, so we're going to run it. Now they were nice and they gave us most of it, so we could have just done the stats. And mu1, and we got to change my HA my HA is going to be what? Greater than. And pooled, we always say no. Okay? And so my test statistic is negative 1.61. My p-value is, I typed in wrong. My p-value, sorry, this is going to be positive 1.61. So positive 1.61. Oh, whoa, I got to go back. This is a reduction. This is mu A is less than mu B. Sorry, guys. So that's a reduction. This would be a greater reduction than that one. Totally sorry. So p-value then would be, hopefully you were yelling at home to me and I just didn't hear you. So then this would be 0.062, I think, if I'm doing my math right. I have to kind of work off my messed up one. But at any rate, our decision would be that 0.062 is greater than 0.05. So what do? Fail to reject HO. There's not enough evidence at alpha equals 0.01 to say the true mean reduction for the drug is greater than placebo. All right, and I know I'm stuck in that little corner there, but there you go. So again, if we kind of talk about a couple of things, could I have made a type 1 error or type 2? Well, what was my decision? Failed to reject, so we could have made a type 2 error. Type 2 is when we fail to reject the null, when the null hypothesis is false. All right. Okay, so we got about 8 minutes left. We'll keep going on. So what I wanted to do next was to show you a matched pairs test. And this is the same woman, or this is the same car model being sold to by a man and a woman. Look, the purchase price and the difference. 8 randomly selected car models. What do you notice? How is the data set up, everyone? Car model 1, woman, man. Is this value independent from this one? Could I switch this $20,000 and this $46,000? Could I switch this Civic and this Beamer? No, because that's the car. It's dependent upon the car. So these are now not independent. And when they're not independent, they're dependent, then we are going to analyze the differences. So this would be a matched pairs t-test. Well, how do you run that? Just like a regular t-test. Okay, my HO is going to be mu D equals 0. My HA would be that mu D, in this scenario, that women pay more than men is greater than 0. But in my calculator, there's no matched pairs test. I'm the statistician. I understand that I'm going to run this as a regular one sample t-test. And I've got this here, so I'm just going to run it real fast. So menu, stat test, regular t-test. And I know that at the end of this thing, oops, that's because I don't want that. I want that to be 0. I know at the end of this thing that, let's see, we want it greater, that I know that it's paired data. So there's my test statistic. There's my p-value. Clearly, we would reject, right? 0.008 is pretty small. What error could I have made? I could have made a type 1. But again, we don't say that in here. We're just reviewing those topics. Okay. All right, still checking the questions. Nobody's really asking much, so we're going to keep moving on. Okay, number 11. Okay, this is asking us, there's a whole blah, blah, blah in the beginning. Assume the conditions for inference are met. Construct and interpret a 95% confidence interval for the proportion of all adults in the U.S. who would have chosen the economy statement. So p hat is 0.37. N is equal to 1048. So we would do all of our panic here. And again, if you're my students, you know, but we'd have to define our parameter, which in this scenario would be pi or p, depending on how you write it. A would be assess the conditions. We were told they were good. So name the test. This is a 1 proportion z interval. Remember my formula, p hat plus or minus z star, square root of p hat 1 minus p hat over n. Okay, 95, so we go 0.37. 95 is 1.96. 0.37 times 0.63 out of 1048. I don't know what that is. I'm just going to make up a number here real fast. I'm going to say 0.312 to 0.43. I'm just made up because I want to interpret this. So we'd say at the end, we're 95% confident the true proportion of all adults. Remember, that's what a confidence interval is estimating. Pi, the true proportion of all adults. Of all adults that are interested in the economy statement. All right, and that's really all I'm going to get through here. Just talking about B. One condition is that n times p is p hat's bigger than 10, and 1 times 1 minus p hat's bigger than 10. Remember, that's normality of sampling distribution. Okay, so that's what that one is. So again, if you're just taking a look at this later on, I got a couple more questions I just want to try to hustle through. We're going to skip number 12. That one's just not going to work. I want to talk about 13. They give you the confidence interval, and they ask, does it provide convincing evidence? So look, subtract that. It'd be 0.09 to 0.21. Is there convincing evidence that it is not working? So however the owner is concerned, so 0.2 is what we're interested in. And what do we notice? The question is 0.2 in the interval? Yes. So therefore, is there convincing evidence? No. 0.2 falls in the interval. So it's a plausible value. Plausible value of pi. Okay, so there we go. And then determine the value of the margin of error. Again, I don't think we have time. We got 3 minutes to this. But then the last one is they increase the sample size 4 times. So remember, the standard error would be cut in half. You take the square root of 4, and it'd be 2. So you see that it would be cut in half. All right. So again, all you'd have to do for this one is just cut that, literally just cut it in half. That's all you'd have to do, 0.15 plus or minus 0.03. And now you'd come up with 0.12 to 0.18. And so now would you have convincing evidence? Now you would, because guess what? 0.2 is not in the interval. Okay? All right, and 14, so this one, we got linear regression, talking about wind velocity, all sorts of good stuff. So use computer output to determine the least squares regression line. Remember, you want to circle this little boot here. That's our important stuff. So we want to make sure that this works. So what we're looking at is we're looking at amperes, so our amps hat equals 0.137, that's the constant, plus 0.240 times the wind velocity. Okay. So remember, this is always our y-intercept. It's in front of the constant, slope. S, this is standard deviation of the residuals. Remember, residuals, how far is each point from the line? R squared is our coefficient of determination. Always ignore that one. This is the standard error of the slope, SEB. This is the test statistic, assuming beta equals 0, that there's no relationship, and this is the p-value when the HA is beta does not equal 0. Okay, so just a couple of things. So skipping B, what proportion of variation in electricity production is explained by the linear relationship? This is asking you for R squared, which will be 87.3 or 0.873. Doesn't matter. Is there statistically significant evidence? Yes. Why? Because the p-value is 0. So it means we'd basically never get a sample like this if there was no relationship. All right. So that really brings us to the end. Okay, so there was a question. Is there a difference between saying mean difference and difference of the means? So yes, there is. To sample, think about what it says. Think about your test stat or your HO. It's mu1 equals mu2. That's the difference of the means. Match pairs is mu d, right? Which is what? The mean of the differences. Right? You find the differences first and then find the mean. Now, if you understand your random variable rules, you understand that the means of these are the same. The thing that's not the same would be the variances. That's the part that's really different. So that's why it really matters. But I wouldn't get too caught up on that wording. Okay, any other questions? All right, I know that was pretty fast. Hope you guys were able to hang with me pretty good. Just so you guys are aware, number 15 would be a chi-square test. Chi-square test for, I believe it'd be association, so independence. So just so if you were looking at that one later, you do a chi-square test for independence. So I'll hang out for a second if anybody else has any other questions. If not, thank you guys for being here. I hope again you found this useful. I know it's pretty fast. 15 questions in an hour is moving, but again, hopefully you can go back and pause it, practice, and verify and see if you're kind of coming up with the same stuff. Okay, nobody's asking anything, so I'm going to log off, guys. Have a good night, everybody.